Welcome everybody to Contemporary Math. Today's lesson is on 2.6 Infinite and Countable Sets. But before we get into that, I just want to do a short review on how we can find an nth term formula for a pattern or a set of numbers. So our first pattern here is 1, 2, 3, 4. And you probably all could come up with the next couple terms here, 5, 6, so on and so forth. So what we want to do, because this continues on forever in the same pattern, we want to come up with a formula that's going to describe this entire set of numbers. So the very first thing we want to do is look at the differences between each number. So 1 to 2 is 1, 2 to 3 is also 1, 3 to 4 is 1. So we have this pattern of going plus 1. That 1 becomes the coefficient of n in our formula. So our formula is going to be 1n. Now there's only one other part we have to do. We have to check to see, do we add or subtract anything so that the formula will give us this set of numbers. So what we want to do is always plug the number 1 into this equation right here. So we're going to get 1 times 1, and that equals 1. Then from there, you go ahead and compare that number to the first term in your pattern and see if they're the same. Okay? The difference here is what you need to add to this other side. So because this is exactly the same, we don't actually have to add anything else, and our final answer would just be 1n, or we could just say n. Okay, moving on to our next one. First thing we do, check the differences. So we got 1, 1, 1. That means this is going to be in the form of 1 times n, or you can just write n. Then we're going to substitute the number 1 in for n, right here. So we have 1 times 1, which is 1. Then you compare that to your first term. Okay, the first term was 5, and we got 1. So how do you get 1 to equal 5? Well, you would have to add 4, right? Because 1 plus 4 is 5. So what we're going to do here is add 4 to our nth term formula. So now we have n plus 4 is our final answer. Now we can test this with other terms. Okay, so for instance here n equals 2. So when n equals 2, we should get 6 out of our formula. So we plug 2 in right here. 2 plus 4 is 6. It works. We could try it for another one. Here n equals 3. Okay, so 3 plus 4 is 7. And we got 7. So on and so forth. Alright, let's try another one. Letter C. So here, let's find our differences. This is plus 3, plus 3, plus 3. So if we do 3 in multiple times here, we're going to multiply n by 3. Okay, so hopefully you're picking up on that okay, that whatever the repeated multiple is becomes the coefficient of n. Now the next step is to see what do we have to add or subtract. Okay, so again, here n equals 1, and if I plug 1 in for n, I get 3 times 1, which is 3, and I don't have to add anything to get to 3, which is my first term. So I just leave it there. Let's try another one together. So we find the differences. We get 3, 3, 3. That means it's going to be some sort of 3n. Okay, we're going to plug in n equals 1. So 3 times 1, well, that equals 3, but it needs to equal 5. So how do I get 3 to equal 5? Plus 2. We're going to add 2 right there, 3n plus 2. And again, you can always go back and check. If I plug in n equals 2, I would get 3 times 2 is 6 plus 2 is 8. All right. I want you to go ahead and try letters E and F on your own. You can go ahead and pause the video, and when you are ready, just hit play, and you can see if you got the right answer. All right, for letter E, you should have gotten 2n. The reason? This goes up by 2. When you plug 1 in for n, it gives you 2, which is our first term, so there's no need to add or subtract anything else. For letter F, you should have gotten 2n plus 4. The reason? We're going up by 2. And when you plug 1 in for n, okay, you get 2, and how do we get up to 6? You have to add 4. So that's where that plus 4 comes from. Looking at letter G, here's another one that's going up by 2. So do it along with me. What should we get? 2n. Okay, you have to ask yourself, well, what do I do with that 2n? So what do? Well, you plug in 1, representing our first term. Now what do you have to do with this 2? Well, you compare it with the first term and see what do you have to do to 2 to get that first term. So what do you have to do? Well, you have to subtract 1. Okay, what does that tell us about our equation? Well, it's what we add at the end, and sometimes it's subtraction. All right, letter E. You might also find fractions or rational numbers, not just integers, in these patterns. And so it's a lot easier, rather than looking at the whole fraction, to split it up into numerators, okay, the 1, 2, 3, and the 4, and denominators, 3, 7, 11, 15. Now it turns out that each part, the numerator and the denominator, will each get an nth term formula. Okay, so 1, 2, 3, 4 has an nth term formula of n. That was just like what we did here in letter A. Okay, for 3, 7, 11, 15, we're going to have to come up with one. So we got 4, 4, 4, meaning it's going to be some sort of 4n. Okay, we'll plug in 1. Okay, notice we always plug in 1 here. And it gives us 4. And we'd say, what do we do to get back to our 3? Now we subtract 1. So we get 4n minus 1. Now all we have to do, because these were fractions, is make our nth term formula into a fraction as well. And there you go. All right, we're going to be using this now in talking about our infinite sets. First, just a little review. A finite set is a set whose cardinal number is a natural number. Okay, so we just talked about some finite sets, and we were doing most of our set operations with a finite set. So here, if this was our set, A equals ABC, the number of A equals, well, I counted up, equals 3. And 3 is a natural number, and therefore this is a finite set. We can give it a specific number here. We're also going to be talking about this idea of one-to-one correspondence. And it's two sets with the same cardinal number, and basically each element can be paired with another element. So if I have this set A, which is A, B, and C, okay, go ahead and just create another set on your own that would have one-to-one correspondence with this. It can be anything. I'm going to do this. Capital A, capital B, capital C. Okay, so what makes this have one-to-one correspondent is each element will correspond to another one. So the B with the B and C with the C. Okay, so that's 1 to 1. Okay, notice here the number of elements in B also is 3. We're also going to be using the term proper subset. So all elements of one set are in the other, but they aren't equal. Okay, so when we think about this, let's just create another set. We'll just call this set C. And we're just going to make it the numbers 1 through 5. So if we wanted to make a proper subset P out of this, we could choose any of these 5 letters, but not all 5 of them. Okay, so we could just pick like 1, 3, and 4. And then we could say that P is a proper subset of C. Okay, so all the elements in P are in C, but they aren't equal. Now, one thing you noticed about equal sets is that they always have the same cardinal number. Okay, so in this case, these would be equivalent, but equal sets also always have the same cardinal number. So using this information, we're going to define an infinite set now. So an infinite set is a set that can be placed in a one-to-one correspondence with a proper subset of itself. Okay, so placed in a one-to-one correspondence with a proper subset of itself. So let's think about what that means for a second. One-to-one correspondence meant, okay, 2 sets with the same cardinal number, and each element can be paired with another element. So we're going to be looking at a set, and we're going to be pairing it with an element in a proper subset of itself. Now we also said that proper subset can't be equal. So this is where the idea of infinity comes into play. So if we have So let's take a look at our first example, and you'll see what I mean. So we want to show that n, the natural numbers, 1, 2, 3, 4, and so on, is an infinite set. So here's what we have to do. We have to establish a one-to-one correspondence between the set and a proper subset of itself. So right off the bat, we want to rewrite the original set and write its nth term formula. So the original set here is 1, 2, 3, 4, dot, dot, dot. And do you remember this nth term formula? It's going up by 1, so it's just n. And since we start at 1, we can stop there. Now what we want to do is remove the first element from our set. And what this is going to do, it's going to guarantee that it is going to be proper, because it won't be equal because it won't have your first element. So we're going to cut out the 1, and we're going to start at 2, and we're going to write it beneath the first set. Okay, so what we're doing here is we're creating that one-to-one correspondence. So the 1 will correspond with the 2, and we know this set is not going to be equal because we're missing the 1. Okay, so next off, we're going to correspond the 2 with the next element in the set, the 3. The 3 will correspond with the 4. The 4 will correspond with whatever the next term in the set is, which is 5. Okay, so this is what we just did. We placed a new proper subset directly beneath the set by removing its first element and sliding all the elements to the left. Okay, so you see that? We had this 1, and we got rid of it, and we just did 2, 3, 4, and then added our 5. Now lastly, we have to create a new nth term formula to relate the two sets. Okay, so basically, we're going to look at 2, 3, 4, 5 and create its nth term formula. Okay, so the difference here, these are going up by 1, so this will be n. If we plug 1 in for n, it gives us 1. How do we get up to 2? Well, we got to go plus 1. Well, the last thing you have to do is equate the nth term formulas, and then you're fine. Okay, so this is how you show that a set is infinite. So let's try number 2. Show that the set of all even numbers, 2, 4, 6, 8, is an infinite set. Okay, so let's go through this. You can go through it with me here. Step 1, rewrite the set. Okay, include an nth term formula here. So these are going up by 2. So it's 2n. Okay, if we plug 1 in for n, we get 2, which is our first term. So that's all we need. Then directly beneath it, we get rid of the 2, which is the first element in the set, and we start with the 4. We're going to go 4, 6, 8, and we continue the pattern one more, 10. Okay. And then we make a new nth term formula for this set. Now, the way it's going to work is it's always going to have the same beginning. So since this was 2n, our beginning here will also be 2n. Okay, so we got the 2n because this is going up by 2. When we plug in 1 for n, that gives us 2. Okay, and then we have to say, well, how do I get up to a 4? We have to add 2. And lastly, we just want to show that this is one-to-one correspondence by drawing our arrows in. And then we're done. All right, go ahead and give 3 a try on your own. You can pause the video, and when you're done, check back to see if you got the right answer. Alright, so let's check this answer here. So again, we have our first set listed, 6, 11, 16, 21. We create our nth term, so these are going up by 5s, so we got 5n. We plug in 1 for the first term, well that's 5. How do I get up to 6? You add 1. Then we drop our first term and start with the 11. We go 11, 16, 21. Okay, we had to add 5 to get my 26. Okay, now you'll notice here that this just added 5 to each term here. Okay, you guys see that? So 6 to 11 is plus 5, 11 plus 5 is 16, 16 plus 5 is 21, 21 plus 5 is 26. So here's an easy way to get this. All you have to do is add 5 to your first nth term formula, and you get 5n plus 6. Okay, so that's a pretty neat trick that works here. So you should have gotten 5n plus 6. So let's just see that that works everywhere here. So you had your 1, 2, 3, 4, n. You got to come up with that. You get rid of the first term, start with the 2, 2, 3, 4, 5. Okay, notice what we did here. We just added 1. So all you have to do is add 1 here, and you get your nth term formula. See if it worked with the evens. 2, 4, 6, 8. We had to come up with the 2n. We get rid of the 2, start with the 4, 4, 6, 8, 10. How do we get from 2 to 4, 4 to 6, 6 to 8, 8 to 10? We add 2. So all we had to do is take this formula and add 2 to it. Okay, so that should help you out. All you have to do is find that first nth term, and then finding the second one is easy. You just add whatever you had to get there. All right, so that is showing that a set is infinite. We're going to move on now and talk about sets being countable and learn what Aleph-Null means. So there are two ways a set can be countable. First is it can be finite, meaning you can count the elements. The other way is it can be placed in a one-to-one correspondence with the set of counting numbers. So that makes sense, right? If you can count something, you can say, well, this is the first element, the second element, the third, so on and so forth. So that's what we're going to do here to see if a set is countable. Now, Aleph-Null, this is a special type of infinity, and it's the cardinal number of an infinite set. So if I gave you the set 1, 2, 3, 4, ... and I asked you how many elements are in this set, you would say, well, the number of elements in the set is Aleph-Null. So it's just kind of slanted line, and then a little squiggly here, and a little squiggly here, okay, with the 0 here. And this is the lowest order of infinity here when we talk about infinite sets. So this set has this many elements. We call it Aleph-Null. So our first question says, show that the set of even counting numbers has cardinal number Aleph-Null. Okay, so they didn't give us a set here. They just said even counting numbers. So we should know what that is. So let's come over here to our directions and see what we have to do. So it says, to show a set is countable and has cardinal number Aleph-Null, you must place the set in a one-to-one correspondence with the counting numbers. So what you want to do is list the counting numbers. So that's always the first place to start. We got 1, 2, 3, 4, ... And the counting numbers are always just going to have n as your nth term formula. Then we're going to list the set below the counting numbers and add its nth term formula. So the set here is even counting numbers. So we have 2, 4, 6, 8. Now you can see that we're creating a one-to-one correspondence with the set of counting numbers. So we're showing that this set is countable because every time we get a new number, we know its position. So the last thing we have to do here is write the nth term formula of our set. Well, we've done this one a couple times, so even counting numbers go up by 2, so we get 2n. And since we started at 2, we don't need to add anything else. Okay, and because we can equate n to 2n, we know every number is going to be placed in a one-to-one correspondence with the counting numbers. Therefore, this one has cardinal number Aleph-Null. Okay, just like this. So when you work out your problems, this is what I want to see. I want to see the counting numbers with the n. I want to see the set in question, okay, placed directly beneath with its nth term formula. I want to see the arrows for the one-to-one correspondence. And then I want to see this. Okay, the number of elements in the set is Aleph-Null. Okay, I want you to try number 5 on your own. Go ahead and pause the video. And when you're finished, hit play. You can check your work. All right, let's check how we did. You should have the set of counting numbers listed here with the n. Then you should have the set of odd numbers listed below that, and its nth term formula should be 2n minus 1. You should have your arrows here showing the one-to-one correspondence. And then just your final answer, the number of odds is Aleph-Null. All right, question 6. This is just to kind of get your brain thinking a little bit. It says, what is the union of the odd counting numbers with the even counting numbers? Okay, so if we took set O and united it with set E, okay, this would give us all the counting numbers, right? So 1, 3, 5, 7, and we join that with 2, 4, 6, 8. So we join these two sets and we get the natural numbers. Now we just showed that the odds have Aleph-Null elements and the evens have Aleph-Null elements. Okay. And we also know that the natural numbers would have Aleph-Null elements. So it's kind of weird because we can say that there are the same amount of odd numbers as there are even numbers, and that also equals the same amount of natural numbers. And so it's a very weird thing. Okay, so Aleph-Null is any set that is countable and infinite, and it is the lowest order of infinity. Don't stress too much about that. You can look it up if you want to look up orders of infinity. There's a lot of interesting stuff out there about this if you're interested. Other than that, as long as you can do the basic stuff, that's all that's going to be required for this course. Again, thanks for watching, and I'll see you back in class.